satellites are remote sensing tools. Remote sensing just means that if you have an instrument that measures a certain subject or phenomenon, it doesn't have to make contact with that specific subject or phenomenon. It can measure the characteristics of that phenomenon from a distance. There are two main remote sensing tools that we use in meteorology: radar and satellite. Both of these use electromagnetic waves to make their measurements. Electromagnetic waves are just waves that have an electric field and a magnetic field that move through space. We kind of touched on this in the radar module. If you haven't seen the Radar Foundations module, go ahead and check that out in the Chaser Academy. But satellites and radar use different types of electromagnetic waves. Now, these waves come in different wavelengths. The wavelength of an electromagnetic wave, or any wave for that matter, is the distance from the crest of one wave to the next. There are several different types of electromagnetic waves, each with a different wavelength, and that creates what we call the electromagnetic spectrum. This is just a spectrum of all the different wavelengths of electromagnetic energy there are. A couple things to note: every object in the universe emits some kind of radiation, whether it's a tree, a house, a car, the sun, a skin cell. Doesn't matter. Every single object in the universe emits some type of radiation. And also, the shorter the wavelength of an electromagnetic wave is, the greater the energy is in that wave. So we'll start at the top here where your longest wavelengths are found, going all the way down to the bottom where your shortest wavelengths are found. Your longest wavelength energy is going to be radio waves. So AM radio, FM radio, microwaves, and radio waves are what Doppler radar uses to measure the characteristics of their targets. As we talked about in the Doppler radar module, the wavelength of energy that's emitted by Doppler radars is on the order of a few centimeters at most. So those are your longest wavelength waves. Those are going to be radio waves. Also, objects like a house, for example, that is going to emit long wave radiation as well in that same portion of the spectrum. Then we go down the spectrum to shorter wavelengths, for example, ultraviolet radiation. That's going to be what the sun emits. X-rays as well. And then your shortest wavelength energy is going to be gamma rays. This is the energy that's emitted via radioactive decay. So if you were to go down to the basement of the Chernobyl nuclear power plant toward the elephant's foot, that's emitting a massive amount of gamma radiation, which is extremely toxic to humans. Now, the only portion of the electromagnetic spectrum that we can actually see with the naked eye as humans is in this tiny portion called the visible portion of the spectrum. These wavelengths correspond to light, and different colors are going to have slightly different wavelengths. So the wavelengths that are coming through in the sky that cause the sky to be blue are going to have a slightly different wavelength than, say, an open flame or fire. That's going to be more of your orange and yellow wavelengths, which are slightly different than the blue wavelengths. Different materials absorb certain wavelengths of energy, including the atmosphere. This is critical to how satellites work. Not all the radiation from the sun reaches the Earth's surface, and not all the outgoing radiation from the Earth's surface goes back out into space. Some of it is absorbed by the atmosphere, while other wavelengths pass through. These particular wavelengths, these portions of the electromagnetic spectrum that are able to pass through instead of being absorbed, these are called atmospheric windows. These atmospheric windows are sensed by satellites, which allows us to get a peek into the atmosphere. We can look at the atmosphere using various wavelengths, each of which allow us to get different information about the weather that's ongoing below. There are 16 different atmospheric windows or wavelengths that pass through that the satellites can sense. These are called bands or channels.
Safety is king. That's why these rules are not optional. Free ebook link in description.
Now, there are two main types of weather satellites, the first of which is called polar orbiting. As its name suggests, a polar orbiting satellite orbits latitudinally over the poles. They're situated about 500 miles or so above Earth's surface, and they orbit the Earth about 14 times per day. Polar orbiting satellites are very good at giving us highly detailed imagery of the poles, but not so much the rest of the globe. This is where the second type of weather satellite comes in, which are called geostationary satellites. Geo meaning Earth, stationary meaning not moving. So, Geostationary satellites hover continuously over a single fixed location on Earth's surface. Essentially, they're synced to Earth's rotation, so they orbit just once around the Earth per day. This provides us with a lot of advantages. Geostationary satellites can give us continuous coverage of certain regions at all times of the day due to the geostationary nature of the satellite itself. They can record images much more frequently than polar orbiting satellites. Geostationary satellites can give us new images up to every minute. And because they're focused on a fixed location on Earth's surface, we can analyze the actual motion of the clouds below, which of course is highly critical to severe weather forecasting and nowcasting. Now, geostationary satellites orbit at an altitude of about 22,000 miles above Earth's surface, so they're not quite as high resolution as polar orbiting satellites, but with the advances that have been made in the past few decades with geostationary satellites, we can still get very high resolution data of a much larger chunk of the globe than polar orbiting satellites can give us. And the numerous advantages that geostationary satellites give us really outweigh those of polar orbiting satellites. The main satellites we use for weather forecasting here in the US are the GOES satellites. GOES stands for Geostationary Operational Environmental Satellites. Chances are any of your favorite weather data sites that offer satellite data, they are going to show you data from the GOES satellites. There have been several iterations of the GOES satellites since GOES 1 was launched in 1975. Today we're up to GOES 18 and GOES 19. The GOES suite is occupied by two main global sectors, GOES East and GOES West. Essentially, these are the two main fixed locations above which the satellites are hovering. The GOES East position is currently occupied by the GOES 19 satellite, while the GOES West position is currently occupied by the GOES 18 satellite. Zooming in on our full GOES West sector, you can see how expansive it is. The GOES West and GOES East sectors make up over half the globe, so we have quite the vast expanse that we can analyze using satellite imagery from the GOES satellites. Note that the resolution is somewhat degraded near the poles, but elsewhere the resolution is quite high. And because the resolution is so high, we can zoom into even smaller sectors that give us a really honed-in look at much smaller regions, which of course is quite useful for severe weather analysis. Typically, in these smaller sectors, new imagery will come in every 5 minutes, but on big severe weather days or for tropical cyclones, we can use the mesoscale floater sectors. These mesoscale floater sectors move around. So, based on where the best chances for severe weather are or where the tropical cyclone is located, these sectors move around. Now, what's nice about these mesoscale floater sectors is that the new imagery comes in every minute, which gives us an even higher temporal resolution look at the data and can allow us to see really intricate changes in these systems over a short period of time.
Remember to check out those links in the description below, and then watch another video.